Now, we have learned that there are Hermitian operators that satisfy the condition that if it is the same as, so it does not matter whether you put it in the left or in the right. And on what basis did we arrive at this? We argued that any observable, it must have its expectation value real number. That's where we started, and we arrived at this. But then there is also another important demand of quantum mechanics. While talking about the postulates of quantum mechanics, I said that you can ultimately observe the eigenvalues of an operator. That means these are the ultimate observables. You cannot observe anything other than the eigenvalues. And therefore, the another requirement of quantum mechanics is that the eigenvalues should also be real numbers, because you have to observe them, right? So let us see whether this condition that also ensures that the eigenvalues are observable. Okay. So you assume that A is the operator. So A is the operator with must have eigenvalues and eigenvectors. So let us consider two eigenfunctions. Phi I of x and phi j. Not using psi because psi is reserved for the eigenfunctions of a particular potential function. So this is a general scenario I'm talking about. So I'm just writing phi I and phi j. Okay. So we can now then write, since this is a Hermitian operator, I can phi j a phi I, okay, and that should be equal to a phi j phi I, okay, because of this character that I can put the operator either in the right hand side or in the left hand side. It is the same thing. Now this is, since A is the operator whose eigenfunction is this, therefore this side is nothing but times eigenfunction. So we can write phi j, this will be ai, the eigenvalue, phi I is equal to, this will be a j phi I. So this is again A operating on phi j is aj phi j. Okay, aj is the eigenvalue corresponding to this eigenfunction. Now I'll take this out. Now when I take this out, it is in the right hand side, it is in the ket side, and therefore I can just take this one out. It is ai phi j phi I, and this is in the bra side, and therefore when I take it out, it has to be conjugated. So it is a j star phi j phi I. Okay. I can then put this one here. I can write ai minus aj star phi j I is equal to 0. Now, here are two things whose product is equal to 0. Therefore, either of them must be equal to 0. And I can see there are two conditions, I is equal to j and I not equal to j. First, let us consider, let me get some space. For I equal to j, then if I equal to j, then this definitely is not 0. Okay, because this is a, if it is a that will be 1. So this must be equal to 0, and therefore, so this will be phi j phi I is definitely not equal to 0, and therefore that yields that A, and since I is equal to j, I can write is equal to AI star, which immediately means that AI is real. Okay, so the eigenvalues, if this is satisfied, then eigenvalue must be real. The other implication is that for I not equal to j, then these are orthogonal, and therefore these will be I phi, phi j phi I should be equal to 0, and that means for this is for AI not equal to AJ. Then, assuming that the eigenvalues are non-repeating eigenvalues, then these must be orthogonal to each other. So these are orthogonal. Sorry. Okay, so this is an important result, that we have ensured that whatever we will observe are real valued, and we have also ensured that any two eigenvectors of a Hermitian operator are orthogonal. This is a very important result because that needs to be ensured in order for quantum mechanics to make sense. So now we'll need to work out certain rules of dealing with the Hermitian operators. And suppose we have A as a Hermitian operator and lambda is a real valued constant. Then if I'll put the lambda in the right hand side, lambda A G, this can be written as, I can take the lambda out, lambda, it is F A G, lambda is a constant, and we can then take A to this side, lambda, it is A because it is a Hermitian operator, we can write to this side. This is since A is Hermitian. And then I can put this one back in because it is real. This is, sorry, lambda A F G. This is since lambda is real. Well, then you see that the whole thing, lambda A being in right, is the same as lambda A being in the left. So a real number times is also Hermitian. So we can multiply a Hermitian operator by a real number, and when we do that, we will get a Hermitian operator. This was rule number 1. Rule number 2 is if I have one Hermitian operator and another Hermitian operator B, then is A plus B a Hermitian? Well, let us simply work it out by putting in the same kind of equations. If A plus B G is equal to, now I can break it up because it follows the distributive rule. It is A operating on G plus F B operating on G. This is something we have seen in the last class, that because distributive integrals of a sum is sum of the integral, we can bring to this side and we can bring to this side because these are Hermitian operators. It is A F G plus B F G. And then I can put them together again. It is A plus B F G. Obviously, you can see that A plus B being in the ket side or A plus B being in the bra side, and therefore A plus B is a Hermitian. So this is Hermitian. Finally, is AB Hermitian? Again, we try to work out in the same way. We say if A, B, G. Now, this is actually, you have to realize that what is happening here is that first B as an operator operates on the function G. Whatever you get, A operates on that function. Whatever you get, F and that function are, you take a overlap integral of that. Effectively, that's happening. So it is actually this. First, I'll put a bracket so that you can easily see that B is first operating on G. And so if that be so, I can take the A out here. It will become A, F, B, G. And then I can there. I'll have to be very careful. It is B, A, F, G. So we started with A, B, G, and we ended up with B, A, G. It will be Hermitian if A, B is Hermitian if A and B commute. That is AB minus BA is equal to 0. Okay. Great. So we have, and we have seen situations where AB minus BA is not equal to 0. And P, this is something that you probably have done. So for A is equal to X, B is equal to P, what happens? X, Px operating on f of x is equal to x and then minus del x operating on f of x is equal to minus I h cross x del f del x. And your Px x opposite order operating on fx is minus I h cross del x, then x fx. Now del x operates on this whole thing, and therefore this yields minus cross x del x plus fx. And if you subtract this, these two cancel off, leading to, so your conclusion is that x px minus px x, this whole thing is nothing but I h cross. This is something that you probably saw in the last year. So this is a situation where x and px, two operators, do not commute. Not commute, AB is not a Hermitian, so x px is not a Hermitian. Okay. So now we are considering the observable A. Sorry. Observable was some observable A with operator operator A hat. That is a setting. Only thing I will assume now is that A does not depend on explicitly on time. Not depend on time. What does it mean? It means that, for example, x as an operator does not depend explicitly on time. Px as an operator does not depend explicitly on time. The Hermitian as an operator depend explicitly on time unless the v function, the potential function, is time-dependent function. So we'll consider situations where A does not depend explicitly on time. So x, px, h are all examples of such functions. Okay. And the question regarding the expectation value of A. Expectation value of the observable A. And we know that this expectation value can be obtained by the sandwich integral. It is psi star sandwiching A, and then it is psi x t dx. This is something that you did in the last year, so I'm not getting into the details of it. But this is something, this is called the sandwich integral. These two sandwiching the operator. We're asking, how does A change with time? ddt of the expectation value of A. So I have to differentiate with respect to time the right hand side. And if you want to differentiate with respect to right hand side, we'll notice that there are two things. One is this part, another A of whatever function it results in. And therefore, when we differentiate with respect to time, it can be broken up into two additive terms. It will be minus infinity to infinity. Plus, first we'll differentiate this. It is psi star. I cannot write dd because A, it's the expectation value of A was dependent, a function of time, dependent on time. So we are taking a direct derivative. But psi star is dependent on x and t, and therefore we have to do a partial derivative. It is a function of x and t. And then it is A psi xt plus it is minus infinity to infinity. First, this one will remain psi star xt, and then your A operator. Now, since A operator is independent of time, so we can keep it as it is, and I have the del psi xt del t dx. Sorry, here also there will be dx. Written in the shorthand way, bracket way, it will be delta psi del t a operating on this part plus it is psi. We will not write psi star, right? Because whatever in the bra side is automatically understood to be starred. It is psi a del psi del t. So this is the shorthand, the same thing. Okay, now we know these from the Schrodinger equation. So from the Schrodinger equation, SHR. From the Schrodinger equation, I h cross del psi del t is actually the Hamiltonian operating on psi. This is the Schrodinger equation. And this yield del psi del t as 1 by I h cross h psi. Okay. So let us put this here and here. So which means your I need to look at this. Yeah. I had t dt of a. This was what we are trying to calculate. It will be in this place 1 by I h cross h psi in place of this a psi here plus psi and then a, then we have to write the whole thing 1 by I h cross h psi, right? We are substituted here. Let us bring this I h cross up front. From here, it is going from the bra side, so it will be conjugated. It is going from the ket side, they will not be conjugated. And so it will be minus 1 by I h cross. It will be h psi a psi plus 1 by I h cross psi a h psi. Okay. So now since A is a Hermitian, H is a Hermitian, so I can bring this one here. So the Hamiltonian operator is obviously a Hermitian. So we can write it as minus 1 by I h cross. It is psi, bringing this here, h a psi plus it is 1 by I h cross psi a h psi. Okay. This is equal to, I will now bring this in common, 1 by I h cross. This was plus, so I have to write this one first. It will be psi a h minus h a h minus h a psi. And this is clear that this is nothing but, I can also put it like this, AH minus HA operating on psi. and it is equivalent to put another this here. So this looks like a sandwich integral. The sandwich integral will mean, that this quantity is nothing but the expectation value of this, and this is nothing but a commutator. So this is equal to 1 by I h cross the expectation value of the commutator of an h. This is a very important result in quantum mechanics. So this is called the generalized theorem. What does it say? Physically, it says that the ddt of any variable, any observable quantity A, its expectation value, how does it vary with time? That time dependence is dependent in turn on how that particular operator commutes with the Hamiltonian operator. It's directly related. And a lot of different results follow from this. By putting operators in place of that arbitrary operator A. Let's see. Let's do one by one. First, assume that A, this is the identity operator. What does identity operator means? Identity operator operating on anything leaves that unchanged. But still it is an operator. So let's assume that the A is an identity operator. So what does the generalized Ehrenfest theorem tell us? It tells us that the ddt of the expectation value of this. Now this should be 1 by I h cross, it will be the I comma h. Obviously, I operates with anything or commutes with anything. Therefore, it definitely commutes with this. Therefore, it is equal to 0. What this is ddt of the expectation value of I. Expectation value of anything is obtained by the sandwich integral. And so this is nothing but psi I should be equal to 0. Now I operating on psi leaves psi unchanged. So this is nothing but ddt of now this is interesting. What is this? This is nothing but mod psi square. And this statement says that the mod psi square does not change. And its implication is that if psi is normalized once, it stays normalized throughout its evolution following the Schrodinger equation. So it means that if is normalized, it stays normalized. Good. Okay. Now, any question you can ask? Otherwise, we'll put another variable here and check out the result. I don't have space, maybe. Do I? Yeah, we have space. 2. I'll put A to X. Then what is the result? Okay, that's something we need to look at. If we put A is equal to X, then it says the generalized Ehrenfest theorem says that ddt of the expectation value of x 1 by I h cross the expectation value of the commutator x and h. Right? Now, what is h? H is it is p squared by twice m plus v. You remember that? Okay, I'll put px squared because it is in the x direction. So px squared by twice m plus this, and this is to appear here. You notice that x definitely commutes with vx because vx is nothing but a function of x. A function of x and x itself, this operator is nothing but a multiplication by x. It definitely commutes. So these two commute. Effectively, then we have to figure out if this x square. So effectively, this is we need to figure out this. It is x h. This is what we need to figure out, and this is x p square by twice m plus vx plus minus px square by twice m plus vx x. So it will have two parts. X definitely commutes with vx, so it will not really matter. So we can, in brief, write this as I'll get 1 by 2m outside. 1 by 2m I can get outside. It is 1 by twice m. It is basically the commutator of x and px square. This is what we need to figure out. Now this out, what we'll do is that we'll explicitly write it. So it is x px minus px x, right? Just spare this 1 by 2m because what we are writing is essentially this part. We already know, we have already written that, is that x px minus px x is equal to IH cross. We have done earlier. So x px is IH cross plus this. So x px is IH cross plus pxx. Then px minus, and pxx is, bring this one here, bring this one here, px, I'll keep this one here, and this one I'll substitute by that. It is x px minus x px minus IH cross, okay? So we have just substituted this and that, and then we have landed in IH cross px plus px x px, and here it is minus x px, cancels off, and this is plus IH cross PX. This is equal to, this will be twice IH cross PX. We into this, so I can now write some little more space. Yeah, we can now write dx dt. This is where we started. Is equal to 1 by IH cross comes from here, and then this one, it is basically XH. This is what, let me write, otherwise we might miss things. And then it is 1 by us. There was a 1 by 2m, 1 by 2m, and then we landed into this, and that was this. So into twice IH cross PX. H cross cancels off, I cancels off, 2 cancels. Well, it is this part, so it's value we have to calculate. This is the expectation value of y. This is the first Ehrenfest theorem. Okay, so really the same as the classical result. Classical result is where dx dm, and here in quantum mechanics, this is expectation value. The essential content of the Ehrenfest theorem, that it relates the result of the classical mechanics in quantum mechanics. Now, I'll request you to do the same exercise that we have done by putting A is equal to Px. It will be similar procedure, which will lead to it will be Px is equal to something in the right hand side. Okay, so that you need to figure out what that will be, and follow exactly the same procedure. I leave it as your home task that you will before the next class. Okay, now we'll stop here because it's 5 minutes remaining. If there is any question, we'll answer that and then we'll end. So this part I have left for you to calculate exactly the same procedure, so it's not difficult. Is the operator A hat always independent of time explicitly? No, it is not. This theorem applies to systems where it is independent of time explicitly. That we said that X is not dependent on time, Px is not dependent on time. So these are variables on which it is applicable. The Hamiltonian can be dependent on time. Supposing you have a time varying electric field applied on a particle, then obviously the function will be time varying because V function is time varying. If that is so, then on the Hamiltonian function, this will not be applicable. The TAs need to discuss something with you. Can we stay? Yes, of course. Yeah.
Sir, I have a question.
Yes.
Sir, the operator is not time dependent.
Yes.
But the expectation value of operator is time. When we change, it's changing with time. Expectation value.
No, expectation value is not of the operator. It is the variable associated with the operator. Okay, the operator itself is the variable itself is definitely time varying because X is variable with time. But the operator itself, say X, is the operator corresponding multiplication of X is the operator corresponding to the variable x, and x itself does not contain t in it, right? It's multiplication with x, and therefore it will be considered to be independent of time. We can do what we did with that kind of thing. Px, the momentum is definitely time dependent, but its corresponding operator, momentum itself is time dependent, but the momentum operator by itself is not time dependent, right? Because px, just px, its expanded expression is that minus I h cross del x. That's it. There's no t in it. Therefore, that can also be considered to be a time independent operator. But that does not mean the variable itself is time independent. Yes?
Why is it like this?
Why is it like this means what? Which question?
I mean, why is it like this? Operator is not time dependent, but the expectation value is the time dependent. I mean, why is it like this?
Well, the operator is something that operates on the psi function to okay. Now that itself need not be time dependent. So the variable itself is not the same as the operator corresponding to that variable. There is an operator corresponding to that variable. X multiplication by x is the operator corresponding to the x variable. The same thing. Okay. By this operator, by using that operator, we extract information regarding the position of the system, of the particle. By operating on psi using px, we extract information regarding the momentum of the particle. Operator with a hat time dependent. It's an operator.
Okay.
It's something that operates on a function to give another function. That's it.
Okay.
Any other question? Okay. If not, let us stop today.